Welcome to Module 14. In this module, we'll discuss XSS or cross-site scripting attacks. An XSS vulnerability occurs when users supply data which is transferred to a web application through GET or POST methods is not adequately filtered, allowing for an attacker to inject an external HTML code into the generated page. The HTML may contain embedded JavaScript, which is executed in a victim's web browser. Data, such as session ID cookies, could be intercepted this way. A hacker may also gain access to a victim's computer. The so-called exploit packs are toolkits facilitating the exploitation of browser vulnerabilities. Once a potential victim opens an infected website using a vulnerable browser, the exploit pack installs malware such as Trojans or viruses on the system. XSS attacks are usually divided into two subgroups. Reflected XSS attacks take place when an exploitation string has been sent by a victim's computer through GET or POST whenever they visit a vulnerable page. For example, if the vulnerability occurs in variables passed through the GET method, the victim has to be persuaded to visit the specially crafted website for the attack to succeed. The second XSS vulnerability class is stored XSS. The attack occurs when an attacker is able to save malicious code to a server, for example in a database or a file, which means that a victim doesn't have to be lured to a specially crafted page and can instead be targeted while browsing a normal service, for example while reading website comments or a guest book. Let's now see an example of the reflected XSS flaw. You can see here a simple script which simulates browser actions. Search engines embedded in web applications will very often redisplay the string supplied by users. The same mechanism is employed here. The content of the form is sent via the GET method, and the search result is displayed. Let's see how this script works in practice. As you can see, the string has been displayed. We might notice that user-provided data is not filtered, which means that an attacker has full control over the shape of HTML code, which will be reflected and may use this to inject a JavaScript. All it takes now to execute the code embedded in the link is to send the URL to a victim and persuade him or her to click. Let's now move to another type of XSS vulnerability, stored XSS. You can see here a simple guestbook script. Comments are passed to script via POST and then saved in a database. All comments will be next retrieved from the database and displayed. As you can see, since the script doesn't validate input either, we can expect that it will also be vulnerable to HTML code injection. Since the malicious code will be saved in a database, this would be an instance of stored XSS attack. You can also see here a simple control panel. If valid user credentials are submitted and checked in the database, and the user is logged in, the site will display an appropriate message. Imagine that the browser represents a guestbook administrator. We've logged in successfully. Imagine that the other browser represents a hacker trying to exploit the XSS vulnerability. For the purposes of this presentation, we've created a script which creates a script tag and sets the address of a sniffer, which is a type of software that can capture user-supplied data passed through the GET method. In this case, the sent data is the content of the cookie variable. Finally, the tag is added to the DOM tree. This provokes an attempt to load the script and the sending of the GET request, which will contain cookies. The sniffer PHP file logs all referred parameters to a sniffer log file. The file could be stored in the service which has been taken over by an attacker. In this way, the attacker could obtain access to data stolen from the vulnerable website. In our case, this data is a PHP session ID. Let's copy the script and try to add it to the guest book. As we can see, new elements have been added to the page. The site source code now contains our script. In this case, the code has been immediately executed on the attacker's side. And so the first entry in the sniffer log contains the attacker's session ID. Imagine that a logged-in administrator visits the guestbook page. As you can probably guess, the script which sends data to the sniffer has also been executed on the admin side. The sniffer log file holds admin session ID. Let's try to exploit this. Using the Live HTTP Headers add-on, modify the request sent to the guestbook by setting the stolen admin session ID. As we can see, the attacker has gained control over the administrator session. You probably realize by now how serious XSS attacks could be. How can they be prevented though? The simplest way to do it is to filter all input. User-provided data should be treated with caution, as it could contain malicious elements. If it is not necessary for the users to be able to add HTML tags, we could employ the HTML special chars function. The function converts all special characters used by an HTML interpreter, such as the opening and closing tags or quotes in HTML entities. The entities are displayed normally, but are not rendered by an HTML interpreter. Let's see if setting this function helps. Let's try to exploit the reflected XSS vulnerability once more. As you can see, this time the code has been displayed, which suggests it hasn't been executed. The code of the site contains the AND-LT and GT characters. They are displayed, but not used by the HTML interpreter to identify tags. If you want to allow users to insert HTML tags in your application, using the BB code mechanisms might be a good idea. BB code encloses tags in square brackets and then translates them into individual HTML tags. That's all in this module. See you in the next part of the course. Welcome to this part of the course. In this module, we'll help you understand the concept of XST, or cross-site tracing attack. We found out in Module 14 that XSS vulnerabilities could lead to serious damage. Session ID cookies theft, a usual target for these attacks, had become so common that a special mechanism has been introduced to prevent it. The HTTP-only parameter has been added to cookies, resulting in the sent cookie to be stored in a browser and transferred to HTTP requests, but not accessed by JavaScript. This is served to neutralize many attacks. Let's now see how this mechanism works in practice. You can see here a simple PHP script which sets a cookie and the HTTP-only parameter we've just mentioned. It is initially set to false. We'll cover this part later. Let's now focus on the line which should display the content of a cookie set on the server side. Using the Live HTTP Headers add-on, we're able to see the communication between the browser and user. As you can see, the content of the cookie has been displayed. The contents of the requests includes the set cookie header with the name, value, and expiration date of the cookie. Let's change the HTTP-only parameter to true. Clear the live HTTP headers logs and refresh the page. This time, the cookie has not been displayed and cannot be accessed by JavaScript. As you can see, the HTTP-only parameter has been added to the end of the cookie definition. Virtually all web browsers support the HTTP-only attribute. If it is set by the server, the browsers will block JavaScript access to the cookie, which helps to minimize the fallout from XSS-type attacks. This mechanism was initially believed to be an adequate security measure. A new technique has been developed which serves to circumvent it. This is called the XST, or cross-site tracing method. As we know, HTTP protocol enables sending requests of various types. The most popular among them are GET and POST requests. The head request is also used to query a server for headers only. There are also other types of queries. For example, the trace request, which is implemented and enabled by default in most web servers. The query reflects user headers. All headers sent by a browser, including cookies, are returned as a server response. By using the XML HTTP request object, setting the request type to trace, and submitting the address of the attacked server, an attacker could read the contents of the cookies without using the document cookie variable. Instead, the attack exploits the data returned by text response, bypassing the HTTP-only mechanism. Let's see the site behavior again. As you can see, an error has been reported as a violation of security mechanisms. Many web browsers have lately begun to block less popular and rarely used request types, which could be utilized as a means for bypassing security mechanisms. Disabling trace requests could prevent an attacker from running XSS attacks. This request is used mostly by developers to debug browsers and AJAX requests. However, its use in normal applications is so limited that it seems like a good idea to block it. While today XSS attacks are nearly impossible to launch, it's still useful to keep in mind the possible attack scenarios and to block trace requests at the server level, either in firewall rules, configuration files, or htaccess. That's all in this module. The next module will cover cross-site request forgery attacks. See you there. Welcome to Module 15. In this module, we'll talk about cross-site request forgery, or CSRF or XSRF attacks. A cross-site request forgery attack occurs when a user who is authenticated on a web application is tricked into unintentionally executing an action in the service. A good example of this is persuading an administrator to click a URL which deletes an account of another user. The administrator is, of course, unaware of this. How can victims execute actions without realizing it? This is what could happen if a specially crafted link is clicked and executed through an exploitation of the XSS flaw we've discussed earlier. Let's now take a look at a sample site code which illustrates this scenario. Assume as a starting point the guest book we've talked about in the module on XSS attacks. This unprotected version of the application allows users to submit any HTML code. The second part is an admin script which verifies if an authenticated user has admin privileges. If this is the case, the script enables him or her to add a user holding the login and password indicated with parameters sent through the GET method. If a user who is not logged in visits such a page, an appropriate message will be displayed. The third script enables logins to a service and utilizes the same database table for authenticating users. If the submitted data is valid, an admin session will be activated. You can see here two web browsers with unrelated sessions in progress, which indicates that there are two different users. Assume that the browser on the left side represents an administrator of an attacked service, while the browser on the right represents a hacker who's trying to gain control over the service. As you can see, the attacker is not logged in and is not in possession of a valid login or password, which means that he won't be able to perform any actions in the service. On the left is our admin. Assume he logs in using admin as a username and test as the password. As you can see, the admin has logged in successfully. Let's confirm this. The attacker is still not logged in. Let's now see what a cross-site request forgery attack looks like. You can see here a guestbook script. Let's submit to it an image, which once clicked, will execute an HTTP request to add a user to the service. Let's take a look at the script. We need to pass the action variable with an add_user value. The user variable containing a username and the pass variable with a password. As you can see, an image has been included which hides a link to the admin service in its source. Now, confirm that the attacker is still not logged in and that the account has not been created. As you can see, the account does not exist in the system. Let's assume now that the administrator decides to visit the guest book. The image has not been displayed because its URL refers to a site that is not an image. The administrator could pay no attention to the fact that the image has not displayed, and won't notice that a request has been executed that adds a user to the database. Let's see the result now. A new account has been created for the attacker and he is logged into the service. Try to think of ways in which we could prevent exposing ourselves to these attacks. A good first countermeasure is securing the application against XSS flaws. However, users could still fall prey to such attacks through their websites. To secure an application from performing significant actions in the background in a potential CSRF attack, you can require re-authentication or introduce additionally generated tokens. The database could store random one-time strings, which would be added to all forms generated in a hidden field in a service. This would allow you to check server-side if a submitted token is still active. Thanks to this method, if hackers won't know the currently active tokens, their attacks will be foiled. On the other hand, using only the post method without using GET requests cannot guarantee application security, as an attacker could use JavaScript to generate a post request. That's all in this module. Thanks for your attention, and see you in the next part of this course, which will focus on using a browser to spy on data.